Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 1 for this week. And this entire week, the Monday, Wednesday, and Friday bonus videos are all going to have to deal with weather radar, more specifically Doppler radar, some of the principles of how the radar operates, some of the limitations just based by laws of physics, and some of the newer products that have come along in recent years. So we'll be splitting this up into 3 sections, but today we're mainly going to deal with just some of the basic principles of weather radar. And so let me go on ahead and put myself in the corner here, and we start off with some text information here. So the radar sends out what we call a pulse, okay? And the frequency of the pulse determines how many of these pulses are emitted over a given period of time. So there's actually something called the pulse repetition frequency, or PRF, and this determines how many of these pulses go out and at what time interval they go out. Now, we know that speed is equal to the distance traveled divided by the time that we're looking at, okay? So if you multiply both sides of that equation by time, then you get distance is equal to speed times time. Well, we know how fast the pulse is traveling. It travels at the speed of light, which is 186,000 miles per second, pretty fast. And we also know how long it takes for the pulse to go out, hit a raindrop, or any object for that matter, and then bounce back and arrive at the radar site, okay? So we can measure how fast the pulse is traveling and how long it takes to go out, hit something, and bounce back. We call that an echo, and it's the same principle of you shouting your name in a big room and the sound bounces off the far wall and comes back and you hear it, okay? That's why we call it a radar echo. So if we know both of those things, we can calculate the distance of the object away from the radar, and then we can actually plot that on a map, okay, so that you can see at home if you're watching television or you've got an app on your phone or whatever. That's how those colors are placed where they're placed, because the radar is calculating the distance away from the radar that the raindrops or whatever it's hitting are located. Okay, so here's just a graphical way to represent that, and this is my poor man's representation of a radar, okay? It's actually more of a circular dome, if you will, and then inside of that dome you have the radar that is spinning around, and as it spins around it's sending out pulses in all directions, okay? So here is a cloud with a raindrop falling out of it, and so the pulse comes out of the radar and hits that raindrop and says, oh, I found something out here, let me go back and tell my dad, the radar, what I found. And so it comes back, and again, because we can calculate, or we know the speed of the pulse and we know how long it took to go out, hit the raindrop, and come back, we can figure out how far away the raindrop is. Okay, so here is the Earth, okay, again, a very poor man's representation here, and here is our radar. Now, because the Earth is curved, and I hate to break it to some of you, but the Earth is not flat. We know it is curved, okay? We've proven that over many, many years. So here is the radar up there, and let's say we have 3 clouds that are all located at an equal distance above the Earth, or an equal altitude. So the radar beam goes out, and it has no problem seeing that first cloud and any rain that's coming out of the bottom of it, okay? But as we go farther and farther out, the radar beam doesn't know the Earth is curved, okay? It just keeps heading in a straight direction. So at this point, it's just hitting the middle and maybe the upper portion of the cloud, but is completely missing any precipitation falling out of the bottom of it. And then, of course, by the time we get to the 3rd cloud, the radar pulse is completely overshooting it and missing all of the weather underneath it. And this is why we have a network of radars, the National Weather Service does, all across the country, because you don't want to miss out on something by relying on a radar that is looking at something entirely too far away to be able to detect. And so other radars, other neighboring radars, are much closer to that cloud and they can detect it. And so you take all that information together and you actually can get a mosaic of all the different National Weather Service Doppler radars, and that way you know where all of those raindrops are actually located. There's no danger of missing one unless one of the radars is out for maintenance or has a problem. Okay, so what about the Doppler effect? Because when Doppler radars came along, the big change was that we could not only see where the raindrops were, but whether or not they were moving or not, and in what direction they were moving. And that was obviously critical because if you think about let's say you're at an amusement park and you're looking at a merry-go-round, and one of your kids is on one side of the merry-go-round and one's on the other. Well, at any one given moment, okay, one of your children is moving toward you and the other one is moving away from you, but a couple of seconds later, it's exactly the opposite. But because one's coming toward you or one's going away from you, and a couple of seconds later, it's the opposite, that basically that object is moving around in a circle. So if the Doppler radar detects raindrops moving at high rates of speed in opposite directions close to each other, then that tells us that we have rotation present in that thunderstorm or whatever it is, and that gives us a pretty good idea that there's a tornado present, or at the very least what we call a mesocyclone, which is a rotating updraft in a thunderstorm, which can lead to a tornado, okay? So here we have a human being. Now, the way I'm going to explain this is basically by illustrating it through sound, but it's the same principle, okay? So here's a human being, and you have an object that is sitting up in here, and let's say it's a car horn, but the car is stationary. So it is sending out sound waves in all directions, and eventually those waves reach you over a period of time. But what if that car and the associated horn are moving, okay? So here's your human being. As that object is moving toward you, the waves are bunching up. And that means the frequency of the waves are increasing. And with regard to sound, if the frequency goes up, the pitch goes up. And have you ever noticed that when you're watching a train go by or a car go by that's blowing its horn, you have this effect of, and it tails off like that? Well, that's what's going on here, is that as it approaches you, you're going to have a higher pitch of sound. And then as it leaves you, then the waves are going to be bunched up on the opposite side and farther apart close to you. And so as the frequency goes down, the pitch goes down, and you hear that tailing off effect of the sound, okay? So what happens here with regard to the weather is by measuring the shift in frequency of the pulse, okay, we can calculate the speed of the object and whether or not it is moving toward us or away from us, okay? In this case, the source of the sound was moving toward us, and then once it went on by us, then it was moving away from us, okay? So by measuring that change in the frequency, we can calculate whether or not that object is moving away from us or toward us and how fast. However, there can be an issue here. Here's the radar, here is a raindrop, and as long as that raindrop has some component of motion, either away from or toward the radar can detect what that component of motion is. Now, if it's moving exactly away from or toward the radar, then you get the full speed of that object. But let's say it's moving at an angle like this. So you have the one component of motion moving this way, and you have another one moving this way. It's only going to pick out, or only able to detect, the component of motion that is moving directly away from or toward the radar. And in rare instances, what if the raindrop is moving perpendicular to the direction of the radar pulse? Well, you could have a raindrop moving at 60 miles an hour, but if it's moving exactly perpendicular to the pulse, it will show up as 0, okay? And so you have to be aware of that, or even if it was slightly off being perpendicular, it's going to show a much, much lower velocity than the object is actually moving, because most of the component of motion is perpendicular to the radar as opposed to away from or toward. And again, this is why it's useful to look at surrounding radars, because even if it's perpendicular to the beam of one radar, it's not going to be perpendicular to the beam of a radar in a different location, okay? And so you can, look at those radars and get a better idea as to what's going on with that particular cell or thunderstorm or whatever. And finally, the last limitation I wanted to talk about, and this is simply text that supports what I just said, is something called the cone of silence, where the National Weather Service radar basically starts off at a low elevation, maybe about a half a degree above horizontal, and it swings around, takes its measurements, and then it tilts up a little higher, swings around, takes its measurements, a little higher, same thing. And it goes all the way up to an elevation of 19.5 degrees, okay? And this is so we can get a three-dimensional look at whatever the radar is looking at, which can be very critical when it comes to thunderstorms and the severity of them and whether or not they have the potential to produce downbursts and all this type of thing, okay? So once it gets above 19.5 degrees, it can't see anything, okay? And so if a tornado develops directly overhead of the radar will not detect the tornado. It will have no clue that it's there. And for those of you that were in the Raleigh area back in November of 1988, when we had the big tornado on the Sunday night, early Monday morning of Thanksgiving weekend, we didn't have Doppler radars back then, but even if we had, that tornado actually formed, or as far as anybody can tell, within the cone of silence, and so the radar probably would not have seen it. Now, other radars in other locations could look at it from their vantage point and probably detect it, and once it got far enough away from the radar so that it was no longer in the cone of silence, then the radar would have been able to detect it. But this is an issue with radars. It's, you know, simply one of the limitations that you can't get around, and so as a result, we have to look again at the network of radars to make sure that we're filling in all those holes and we're not missing anything. Okay, that's a lot today. That is bonus weather video number 1 for this week. We will have a look at radar from different perspectives from the one today, coming up on Wednesday and again on Friday. Hope you'll join me for both of those. So you all have a great Monday evening. The daily weather update will be coming up shortly, and we'll see you then. Take care, everybody.